That's why it's pure. However, it's not necessarily completely known to everyone, right? So assuming I prepare a pure state of polarization, and the pure polarization state is in, say, superposition of H and V polarization. So I know what it is, but maybe you don't, and you're trying to measure the variance of some observable, which you define. But remember, you don't know the state. So in general, would the variance be zero? So think of my role as the person who prepares the state. So I prepared this superposition state. I know what it is. So it's a pure state. It's defined, but you don't. But your task is to do a measurement of an observable. So let's call that observable A. And the question is, when will your variance be zero? Or could it be zero? The scenario is, I'm preparing these photons in the same state. I'm giving you many copies of them. Obviously, you need many copies to build up the statistics, right? To see if there's variance. So I'm giving you many copies of the photons. They're prepared in the plus state, which is H plus V, and you're getting them. So if you're asking, are you 0 or 1? Your variance is going to be maximal. So 0 or 1 being H or V, right? Asking the question, are you H or V? You will always get, for each of the photons, 50-50 probability is going to say H, 50-50 probability is going to be V, right? And so your variance is just going to be the maximum value possible. However, if you ask the right question, instead of asking, are you H or V? If you ask, are you diagonal or anti-diagonal? Are you plus or minus? Are you H plus V or are you H minus V? Then you always get the right answer because each one of them is H plus V, right? And so then your variance will be zero. So the answer is, the variance is zero when we ask the right question. So it's zero if the state is an eigenstate of your observable. So this is the way to think of it. It's a nice little example that kind of drives the point home.